All right, so really quickly, let's take a look at your spread plates and the colony counting for them. Just pull your plates out, go ahead and spread them out when you have them. We're going to take a look and we're going to find the best plate to determine the colony forming units per milliliter in your original water sample. Okay, so first we'll take a look at the plates and see what they have to tell us. So this first one here, this is a 10 to the minus 3 plate. Whoever this is, they certainly recognize their writing. Thank you for letting us use your plates. Okay, so you can see 10 to the minus 3, it's very full. A lot of growth there, far too much to count. We're not even getting individual cells or colonies in most cases. So you would just write for that. If you have a pencil that works, thank you. TMTC, too many to count. Make sure you also write your number up here, because you'll need to tell us that. Okay, taking a look at plate 10 to the minus 4 here. A lot of good separation. You can actually start to see the individual colonies in almost all cases, but there are just too many of them. And the reason this is a problem is because when you get so many, they start overshadowing each other, potentially competing for nutrients. You're not really sure that you're getting individual colonies. And with this sort of crowding, it's going to be enough of a factor that it can mess up your count. So it's not just about saving the work and headache. It's less than ideal. It's not reliable. So we move on. And we say for this one, again, too many to count. Okay, so next one, we take a look. Here's a nice number of colonies, nicely separated. You know, there's this bit here in the middle that is sort of growing together, but you can still see the individual colonies and count them well enough to be able to get a good count for this whole plate. You figure, maybe there are about 60, 70, let's say 70 of them, right, in this whole plate. So that's within our range of 30 to 300. Remember, if we get below 30, it's not enough to be statistically significant, and that's what we're seeing here on the 10 to the minus 6 plate. Obviously, great separation. We have a lot of isolation here, but there aren't enough to be able to tell us conclusively how much is in our original sample. So our best plate in this case, then, is the 10 to the minus 5. Okay, so now that you have that, you figured out which plate of yours is the best representation or best estimate of your original microbial load. You just use this to calculate what that microbial load is. So let's go back here and fill this out and say that there are 70 colonies or 70 colony forming units. And then here, instead of too many to count, we had too few to count, right? So how do we determine our microbial load based on these results? Okay, so remember, your microbial load is the number of colonies or colony forming units per milliliter, and we've diluted by a factor of 10 each time. So however many colony forming units per milliliter were here, we have 1/10 as many, 1/100th as many, 1/1000th as many, 1/10,000th as many, and then down here 1/100,000th as many. That's what 1 over 10 to the minus 5 means, right? Okay, so if we want to do the reverse of that, all you really need to do is just take the inverse of this number. Instead of 10 to the minus 5, which equals 1 over 100,000, you would use 10 to the 5th, or 100,000, right? So in order to calculate the microbial load, all we need to do is take our plate count, in this case 70, multiply that by this factor, and we get, we could use scientific notation and do 7.0 times 10 to the 6th, or you could just write it out. 7 million colony forming units per milliliter. Now, ideally, we would use scientific notation for this, and when you get into bigger numbers, which in pure cultures you almost certainly will, this is the way to go. But just to show you, this is what we're looking at. So in our original sample, we have 7 million colony forming units per milliliter. Now this is an approximation just based on what we observed here. Now I'm going to go through this math one more time, step by step, to show you how we got there, so you can understand what happened. Okay, so in our 10 to the minus 5 plate, we had 70 CFUs. Now, if we're going up, if that's 1/10 of a milliliter of this thing, then if we wanted to figure out how many colony forming units per milliliter were in our 10 to the minus 4 dilution, we would divide by how much we added, how many milliliters. So in this case, it would be 70 divided by 0.1, which equals 700, right? So in this tube, you would have 700 colony forming units per milliliter, okay? Hopefully that makes sense. What's happening here is, again, we're just dividing by whatever this is. If instead we'd done it by 200, then we would divide 70 by 0.2, and that would give us a different number. It would give us 350 instead of 700, right? Whatever it is, you just take your count and you divide it by the volume that you put on there, and that gives you the colony forming units per milliliter in the tube that you actually used for it. So that's 700 colony forming units per milliliter in the 10 to the minus 4th. Well, remember, our dilution here was 500 microliters in 4.5 milliliters, or 0.5 milliliters in 4.5 milliliters to make 5 total. So what we're looking at is 0.5 divided by 5 equals what? 0.1, or 1/10. So we have 1/10 as many colony forming units per milliliter here as we do here. So again, we do the same thing. We take the inverse. We just multiply this by 10, which means that we have 7,000 CFUs per milliliter. Now again, if that's because we have this dilution factor of 1 to 10, right? If instead it were different, if it were 2 to 10, let's say that this was 1 milliliter added to make a total of 5, that would be 1 divided by 5, so that's 0.2. Then we would instead divide this number by 0.2, and we would end up with 3,500 for this. So that's the idea. It's not just multiplying by 10 every time. You have to keep in mind what your dilution factor was. And in this case, we just happen to use 10 because it's easiest. All right, so next tube. Again, we have 1/10 as much in here as we do here because we took 1/10 of a milliliter, or 1/10. 1/10 of this came from here. So that means that this is going to be 10 times as concentrated as this one. So we multiply that by 10 to get 70,000 CFUs per milliliter, right? Makes sense. Same here. We get 700,000 CFUs per milliliter because, again, we have 1/10 as much per milliliter here as we do here because we diluted it by a factor of 10. And then going back to the original sample, there's our 7 million CFUs that we calculated the other way, right? So hopefully this makes sense. That's how we're getting to this number. And it's not just a matter of calculating the number of tubes and times 10 or whatever. Keep in mind what exactly you're doing, the dilutions and the dilution ratios that you're using. Hopefully that makes sense because you may or may not be seeing this on the final. So keep that in mind.